today we're going to start talking about a category of compounds called organic compounds. Organic compounds presents a very exciting field of study in chemistry. The reason is that the carbon atom can bond and form many different types of bonds with different substances. Organic chemistry is the study of compounds containing carbon. We take a look at what the properties of these carbon compounds are and the reactions that they are involved with. In organic compounds, we study compounds or materials that contain carbon. Just because something contains carbon does not mean that it is an organic compound. In order to be classified as an organic compound, it has to be made of or by a living being. For example, think of fossil fuels, a huge source of organic compounds. Where do fossil fuels come from? Exactly. So even though those things are not alive right now, they once were. And through the decomposition process, they have created these organic compounds. I've written down some exceptions to things that do not fit into that organic compound category. For example, carbon dioxide, carbon monoxide. Anything that ends in oxide generally is not classified as an organic compound. Instead, we use the word inorganic. As well, ionic compounds containing carbon are not classified as organic compounds either. So this is sodium carbonate. In that case, CO3 2 negative is an ion. No. Generally, organic compounds are carbon-hydrogen compounds. Sometimes they will also include oxygen, perhaps phosphorus, perhaps sulfur, sometimes nitrogen. But they're limited to that corner of the periodic table. Take a look at this. CaCO3, what is that? Carbonate. Okay, so CaCO3 is calcium carbonate. Is that an ionic compound? Yes, it is, because we have a 2 positive calcium ion and a 2 negative carbonate ion. This is an inorganic form of carbon. C25H52. General rule for you is if there's just carbon and hydrogen, it's probably an organic compound. What about Ca2C? It is inorganic because it is an ionic compound. CCl4. What do you think?
Organic.
Why?
Because it's not an ionic compound.
Chances are, if it's not an ionic compound, it's probably an organic compound. What do you think of CH3COOH? Yes, it is. It's actually acetic acid, which is what we use to make vinegar. Acetic acid is an organic acid. I actually have to store this separately from inorganic acids. They're generally incompatible. Even though they're both acidic, I can't store them together. For example, nitric acid and acetic acid should never be in the same cupboard. Ever.
What'll happen?
Let's see if we can find an actual video of that. sure somebody's got a video of them doing it, right? I will look for a video tonight and see if I can find one that will show you.
Can you tell us though? Will it just explode?
It will form compounds that you don't want to inhale because they're bad for you. And it's so reactive you can't control the reaction, and it could result in a lot of heat being released, which could cause a fire. So in our lab, nitric acid is actually stored in its own container, separate from everything. It's in its own Rubbermaid. And then acetic acid is on the other side of the room in its own cupboard, so that there's no mixing of even the vapors. CO2, what do you think? You sure?
No, it was on the other page. Carbon dioxide.
Carbon dioxide. No, this is not an organic compound. Yes, this is not an organic compound. It's inorganic. What about KCN? It is inorganic. That's potassium cyanide. C12H22O11. Any guesses? It is organic. That's actually sucrose or table sugar. Carbon is actually a very amazing atom to work with. What makes it amazing is its electron structure. Because of its electron structure, it is able to combine with a lot of other different things, including itself. So carbon is what we call tetravalent. In order to look at tetravalency, we need to review this structure, which is the Bohr model. How many protons does an atom of carbon have? Okay, so it has 6 protons. How many electrons does it have? In the first energy level, which is closest to the nucleus, you can fit 2 electrons, which means that the other 4 electrons need to go in the second energy level. We put 1 electron on each of the 4 sides before we start doubling up electrons. We say the word tetravalent because there are 4 electrons, 2, 3, 4, in the outermost energy level. A valence electron, or electrons, in the outermost energy level. It is these valence electrons which are actually involved with bonding. The first 2 electrons, they're important. They're obviously part of the structure of the carbon atom, but we're not really worried about them when it comes to bonding. So we are going to use another type of model in order to show just the valence electrons of carbon. The model which shows only the outermost energy levels electrons is called a Lewis dot diagram, or LDD for short. When we show a Lewis dot diagram, 1 dot is equal to 1 electron. we saw on the last slide that carbon had 4 valence electrons. That would be its Lewis dot diagram. How do you know? Yeah. So 2 goes into the first energy level, which means you have 6 electrons remaining. We put 1 dot on each of the 4 sides, and then we double up. How many valence electrons would hydrogen have? Only 1. What about chlorine? Okay, so if we have 17, we have 2 electrons in the first energy level, 8 electrons in the second, 7 in the third. We're only going to draw 7 electrons on the Lewis dot diagram for chlorine.
Insanely high number. Like, let's say there's more than 8 in the outermost level.
That is the limitation of the Lewis dot diagram. We only use the Lewis dot diagram to show up to 8 valence electrons. We do this to show the building of molecules to fulfill something called the octet rule, or the rule of 8. If something has more than this number of electrons in its energy level, we'll use the quantum mechanical model to represent this, and we'll look at that model as a source of inspiration in terms of how does it actually connect with another atom. How many valence electrons will nitrogen have? Well, 5. Okay. Nitrogen has 7 electrons. 2 electrons go in the first energy level. 5 electrons go in the second energy level. 1, 2, 3, 4, 5. There is a shortcut to determining the number of valence electrons that an atom has. On my table, I have something called a group A number. Group A numbers reveal the number of valence electrons. 1A means that anything in this column has 1 valence electron. 2A, anything in this group has 2 valence electrons. Then we have all these B's. We generally don't show Lewis dot diagrams for B substances. We look to the quantum mechanical model to represent these ones. 13 is 3A. These have 3 valence electrons. 4A, 4 valence electrons. 5A, 5 valence electrons, and so forth. A quick and easy way to figure out your valence electrons. Your groups are not labeled with A numbers. What I would like you to do is take a couple of minutes and fill out the A numbers on top of your columns so that you have this shortcut. Within these Lewis dot diagrams, you will see substances or electrons which are paired, meaning there's 2 dots together, versus electrons that are on their own. Electrons that are paired are given the name lone pairs. These pairs will not be involved with bonding whatsoever. Okay? Where one atom can connect to another atom is when there's a single electron by itself. So here, here, and here are potential connection places between nitrogen and something else. For example, chlorine has one opening over here, and by sharing this electron with this one, it can connect to the nitrogen.
So as long as it has an open spot, like they aren't all filled and has an open spot, it can connect with something else with an open spot?
If you take a look at carbon, carbon has the most open spots. It can form 4 bonds. There are 4 electrons by themselves. So that's 4 potential places for connection. So the Lewis dot diagrams show us what we call the bonding capacity. A single electron on one side of an atom will indicate that another electron is able to be shared with that lone electron. Since carbon has 4 single dots, one on each side, that means that there's a lot of potential to create bonds with itself or with something else.